Hydraulic system evolution. The mastery of fluid dynamics represents one of the most profound and transformative achievements in the history of human engineering. Long before the widespread adoption of electricity and the construction of national power grids, the transmission of mechanical energy over significant distances presented a nearly insurmountable challenge to the architects of the modern world. The evolution of hydraulic systems, from the rudimentary harnessing of river tides to the sub-micron precision of modern aerospace valves, is a narrative of relentless innovation. It is a story of how humanity learned to capture, pressurize, and perfectly control the flow of liquids, thereby laying the invisible foundation for the Industrial Revolution, modern urbanization, and the aerospace age. This comprehensive historical analysis traces that evolution, beginning with the ambitions of Victorian engineers and concluding with the digital hydraulic interfaces of the 20th century. Harnessing the river, the birth of urban fluid power in London. The earliest attempts to capture and distribute fluid power were entirely dependent on the natural, unyielding kinetic energy of flowing river bodies. The conceptual seeds for urban hydraulic networks were planted in the late 16th century when engineers first sought to capture the power of the River Thames to serve the growing needs of London. A pioneering example of this ambition was the London Bridge Waterworks, established in 1581 by a Dutch or German-born engineer named Peter Moritz. By securing a 500-year lease on the northern arches of London Bridge, Moritz installed massive water wheels that were driven directly by the fierce, rushing tidal currents of the river. This system utilized the river's kinetic energy to operate rudimentary pumping mechanisms, which raised Thames water into a towering wooden structure. From this height, gravity forced the water down through a sprawling, primitive network of hollowed-out elm wood pipes, supplying thousands of surrounding homes and businesses. While the London Bridge Waterworks was an engineering marvel for its time, it was an inherently limited, low-pressure, open-loop system. It was entirely constrained by the unpredictable nature of river tides, the structural weaknesses of wooden infrastructure, and the constant threat of urban disaster, famously demonstrated during the Great Fire of London in 1666, when desperate citizens broke the wooden elm pipes to access water, causing a total collapse of system pressure. As the British Empire expanded and the Industrial Revolution accelerated into the early 19th century, the physical infrastructure of London reached a critical breaking point. The Port of London descended into absolute pandemonium, choked by the sheer volume of ironclad steamships, frequent vessel collisions, and the relentless influx of global trade. The construction of massive new maritime infrastructure, such as the East and West India Docks, and later the monumental Victoria Dock, spearheaded by George Parker Bidder in 1855, provided deeper shores and vast cargo berths. However, physically offloading the staggering wealth of the empire from these colossal vessels required mechanical power on an unprecedented city-wide scale. The prevailing technology of the time, individual coal-fired steam engines, was highly polluting, dangerously explosive, and required massive amounts of space at every single dockside crane or factory hoist. The radical solution to this crisis emerged not from the sky, but from a labyrinth carved beneath the cobblestone streets of the capital. In 1883, the London Hydraulic Power Company was formally established under an Act of Parliament, merging earlier localized efforts spearheaded by visionary engineers like Edward B. Ellington. The London Hydraulic Power Company represented a total paradigm shift in urban energy distribution. Rather than relying on thousands of isolated steam engines, the company generated immense power at centralized pumping stations, such as the renowned Wapping Hydraulic Power Station. These stations utilized massive steam engines to pump water drawn directly from the Thames into a sprawling subterranean network of cast iron and steel mains, pressurized to an astonishing 700 pounds per square inch. This silent, invisible web of liquid power eventually expanded to encompass over 150 miles of underground piping. It navigated the complex geography of the city by running beneath the Thames via the Tower Subway and the Rotherhithe Tunnel, and crossing major thoroughfares like Vauxhall Bridge and Waterloo Bridge to serve both the northern and southern banks. The impact on the urban landscape and the daily operations of the metropolis was entirely transformative. High-pressure hydraulic water became the literal lifeblood of Victorian London, pumping over 32 million gallons a week at its zenith in the 1930s to power machinery with unparalleled reliability and quiet efficiency. It drove the massive dock cranes that unloaded cargo, operated the heavy printing presses that democratized daily newspapers, powered the complex revolving stages of the London Palladium and the London Coliseum, and even managed the massive safety curtains at the Theatre Royal Drury. Crucially, this pressurized subterranean network gave rise to the widespread adoption of the hydraulic street elevator, a technology that would forever alter the trajectory of urban architecture. Before the advent of safe, reliable, and powerful lifts, building design was strictly limited by human endurance. Commercial and residential structures rarely exceeded the number of stairs a person could comfortably climb, typically halting at 4 or 5 stories. The hydraulic lift, continuously powered by the unrelenting pressure of the London Hydraulic Power Company's mains, completely severed this vertical constraint. It allowed buildings to grow ever taller, fundamentally changing the density, real estate economics, and skyline of the city, while simultaneously democratizing access to upper floors for the general public. To ensure this miraculous system did not succumb to the brutal English winters, the Thames water circulating through the cast-iron arteries was meticulously filtered and actively heated at the pumping stations, preventing the catastrophic freezing, expansion, and rupturing of the pipes beneath the city streets. The Accumulator breakthrough, freeing power from the riverbed. The magnificent triumph of the London Hydraulic Power Company and the widespread adoption of fluid power across the British Empire would have been physically impossible without a fundamental prior leap in how mechanical energy was stored and regulated. For centuries, the primary mechanism for extracting useful work from water was the traditional open-loop water wheel. While water wheels were the essential prime movers of the early factory system, providing the necessary rotational energy for grinding grain, pumping mines, and spinning textiles, they were plagued by inherent and inescapable geographical flaws. They were strictly bound to the immediate vicinity of a rapidly flowing water source, and their energy output was entirely at the mercy of seasonal droughts, freezing winters, and the immediate kinetic force of the stream. Furthermore, as the brilliant 19th century engineer and industrialist William George Armstrong observed during a fateful fishing trip on the River Dee in 1835, traditional water wheels were terribly inefficient machines that wasted vast amounts of their potential gravitational energy. Armstrong, who was originally a practicing solicitor in Newcastle upon Tyne, but harbored a deep, obsessive passion for mechanical engineering, realized that the future of heavy industry could not rely on the continuous, inefficient flow of a river. He envisioned a system based on the controlled storage and instantaneous, on-demand release of highly pressurized fluid. In the 1840s, Armstrong abandoned his legal career entirely to develop the world's first hydroelectric machine, followed shortly by his magnum opus, the hydraulic accumulator. Before the accumulator, engineers attempting to create pressurized water systems had to rely on gravity alone. This required the construction of staggering, monumental water towers, such as the massive Grimsby Dock Tower, where water was pumped to extreme heights simply to create enough static head pressure at the base to operate machinery. These gravity towers were astronomically expensive, structurally vulnerable and limited by the practical heights to which masonry could be built. Armstrong's hydraulic accumulator rendered these towering structures entirely obsolete in a single stroke of genius. The early hydraulic accumulator consisted of a massive, vertically oriented cast iron cylinder containing a precision-machined plunger or ram. This central plunger was heavily weighted, typically loaded with hundreds of tons of iron slag, lead, gravel, or sand, depending on the specific architectural confines of the accumulator tower that housed it. Small, continuously running steam-powered pumps would slowly force water into the base of the cylinder, gradually raising the colossal weight into the air. By lifting this mass, the system effectively stored immense amounts of potential kinetic energy. When a dockside crane operator or a bridge tender opened a control valve to perform work, the sheer, unrelenting gravitational force of the descending weight would drive the water out of the cylinder at an intense, perfectly regulated and constant pressure, regardless of the water's physical elevation relative to the machine. This invention acted as a massive mechanical battery for fluid power. It provided massive, constant pressure and allowed engineers to store energy during periods of low demand, releasing it instantaneously during peak operations. By 1845, Armstrong had successfully installed his first accumulator-driven hydraulic cranes at the Tyne docks in Newcastle upon Tyne, proving beyond any doubt that massive cargo loads could be lifted with silent, effortless precision, free from the immediate proximity of a roaring steam engine. The success was so absolute that Armstrong founded the Elswick Works, building an industrial empire that shipped thousands of hydraulic cranes worldwide. The profound architectural and industrial legacy of this breakthrough can still be witnessed in the surviving accumulator towers scattered across former maritime landscapes, such as the imposing octagonal Limehouse Accumulator Tower in East London, built in 1869 to service the Regent's Canal dock. More famously, Armstrong's accumulator technology became the invisible, tireless muscle behind some of the era's most iconic civic infrastructure. The massive counterweighted bascules of London's Tower Bridge, weighing over 1,000 tons each, were raised and lowered flawlessly for over 80 years by a complex, hidden array of Armstrong's hydraulic accumulators, steam pumping engines, and coal-fired boilers. He even applied his mastery of hydrodynamics to his own sprawling estate, Cragside in Northumberland, which became the first house in the world to be illuminated by hydroelectricity and featured its own sophisticated hydraulic passenger lifts and rotisseries. By perfecting the accumulator, Victorian engineers laid the critical groundwork for the highly responsive, decentralized fluid power networks that would soon reshape global manufacturing. The death of the line shaft, pressurizing the Industrial Revolution. The transition from localized gravity-fed water networks to highly pressurized closed-loop hydraulic systems served as a fundamental catalyst for the maturation and acceleration of the Industrial Revolution. To understand the magnitude of this shift, one must understand the chaotic and dangerous architecture of early industrial manufacturing. In the 18th and early 19th centuries, factory production was characterized by extreme, rigid centralization. Massive textile mills and manufacturing plants were built around a single gargantuan prime mover, typically a massive undershot water wheel or later a multi-story stationary steam engine. This central engine was tasked with turning a continuous, overarching mechanical line shaft that ran the entire length of the factory floor, often suspended dangerously from the ceiling. Every individual piece of machinery in the building, every lathe, every mechanical loom, every milling machine, and every drill press was connected to this singular rotating steel shaft via a terrifying, complex web of rapidly moving leather belts and wooden pulleys. The mechanical line shaft system was inherently flawed, violently dangerous, and terribly inefficient. The entire sprawling network of heavy steel shafts and leather belts had to rotate continuously, consuming vast amounts of the prime mover's energy through sheer mechanical friction, even if only one machine on the entire factory floor was actively being used by a worker. Furthermore, the physical layout of the factory was dictated entirely by the inflexible geometry of the power source. Heavy machines requiring the most torque had to be placed closest to the main engine to minimize energy loss, completely destroying any logical workflow, sequential assembly line efficiency, or safe spatial planning. Moreover, the line shaft represented a catastrophic single point of failure. A single snapped primary leather belt or a mechanical failure of the main steam engine would bring the entire manufacturing operation to an immediate, deafening halt, devastating production quotas. High-pressure hydraulics acted as an elegant, revolutionary escape from the physical tyranny of the line shaft. It was deeply grounded in the principles of fluid dynamics first articulated by the brilliant French mathematician and physicist Pascal in the mid-1700s. Pascal's law, derived during his studies of hydrodynamics in 1648, states that when pressure is applied to a fluid confined within a closed system, that pressure is transmitted equally, instantaneously, and undiminished in all directions, acting with equal force upon equal areas of the container's walls. Because liquids like water and oil are virtually incompressible, they act as perfectly flexible, infinitely malleable rods of transmission. By forcing fluid through a network of small, flexible, high-pressure pipes and heavy-duty hoses, engineers discovered they could transmit massive amounts of mechanical power over vast distances. Unlike a rigid, spinning steel shaft, a hydraulic pipe could be routed around tight corners, buried underground, threaded through walls, and delivered directly to the specific point of application with negligible loss of energy. This capability allowed for the radical and immediate decentralization of motive power. A manufacturing facility could now maintain a single, highly efficient pump house in a separate, isolated building, removing the deafening noise, extreme heat, and fire hazards of the steam engine from the factory floor entirely. Hydraulic lines were then routed to individual, highly specialized machines scattered across the facility. If a particular machine was not in use, the operator simply closed a hydraulic valve. The fluid bypassed the machine, and absolutely no power was wasted on idle friction. This total decoupling of the power generator from the power consumer was a revelation. It allowed industrial architects and factory managers to design shop floors based purely on the logical flow of raw materials, sequential production steps, and human labor efficiency, rather than the rigid mechanical constraints of rotating steel shafts. In this way, the shift to pressurized fluid systems laid the indispensable infrastructural and organizational foundation for true mass production, the modern assembly line, and the exponential growth of global industrial output. The chemical alchemists, transitioning from plain water to specialized oils. Despite the monumental successes of the Victorian hydraulic networks and the brilliance of Armstrong's accumulators, the continued use of plain water as a hydraulic transmission medium presented severe, inescapable flaws that threatened to halt technological progress. Water, while universally abundant, inexpensive, and environmentally benign, is a chemically hostile and physically limited fluid when introduced to the tight tolerances of precision machinery. Its most glaring limitation is its incredibly narrow temperature operating range. If a water-based hydraulic system, such as the outdoor cranes on the London docks or the exposed mechanisms of a bridge, was subjected to the biting cold of a northern winter, the fluid would inevitably freeze. Because water exhibits the unusual chemical property of expanding as it crystallizes into solid ice, a winter freeze would catastrophically rupture thick cast iron pipes, crack expensive cylinder blocks, and shatter precision valves, leading to weeks of costly downtime. Conversely, if the system operated in high-temperature industrial environments, such as near a steel forge, water would boil and vaporize at a mere 100 degrees Celsius. This phase change introduced highly compressible steam bubbles into the hydraulic lines, a phenomenon known as cavitation, which completely destroyed the system's ability to transmit force smoothly, causing erratic, highly dangerous machine movements and severe internal erosion. Furthermore, water completely lacks inherent lubricity. The sliding metal surfaces within high-pressure hydraulic pumps, cylinders, and directional valves experienced rapid, destructive friction when separated only by a microscopically thin film of plain water. To compound the misery of 19th century engineers, water acts as a potent, relentless catalyst for oxidation. It aggressively corrodes iron and steel components from the inside out, leading to scaling, rust, severe particulate contamination, and the rapid, inevitable failure of internal seals. The critical turning point in fluid power technology, the shift that enabled the modern era of heavy machinery and aerospace control, arrived at the dawn of the 20th century. In 1905, an American engineering professor named Harvey Williams and his colleague Reynold Janney of the Waterbury Tool Company revolutionized the field by proposing the total replacement of plain water with petroleum-derived mineral oil as the primary hydraulic medium. They utilized this new fluid medium in the development of their highly efficient axial piston pumps, the famous Janney pump, which were initially applied to the heavy, continuous-duty hydraulic turret steering systems of naval warships. The transition to mineral oil instantly solved nearly all of the inherent, fatal defects of water. Mineral oil possesses a significantly higher boiling point and a much lower freezing point, allowing hydraulic machinery to operate in punishing, extreme environments without the constant risk of phase changes. Most crucially, mineral oil is a natural, highly effective lubricant. As it flows through the pressurized system to transmit mechanical power, it simultaneously bathes the internal moving parts, the rapidly reciprocating pump pistons, the tightly toleranced valve spools, and the smooth cylinder walls in a protective, hydrodynamic film, reducing friction. This dual-purpose capability drastically reduced internal wear, entirely prevented internal oxidation and rust, and allowed engineers to design compact pumps and motors capable of operating at vastly higher rotational speeds and extreme pressures than water could ever endure. However, as the 20th century progressed, the demands placed on hydraulic systems escalated exponentially. The rise of the aerospace industry, the post-World War II global construction boom, and the development of high-pressure industrial injection molding presses pushed basic, unrefined mineral oil to its absolute physical limits. Operating pressures steadily climbed from hundreds of pounds per square inch to several thousands, generating intense internal fluid friction and heat. Under these extreme conditions, basic mineral oils would thin out dangerously, rapidly oxidize, and chemically break down, leaving components unprotected. This urgent industrial necessity birthed the highly complex science of modern tribology and hydraulic fluid chemistry. Fluid engineers realized they had to treat the base mineral oil merely as a blank canvas, blending in highly specialized chemical additives to fundamentally alter and enhance the fluid's physical properties. To combat the dangerous thinning of oil at high temperatures, chemists introduced viscosity index improvers, beginning in the 1930s and evolving rapidly through the 1950s and 1970s. These additives utilized complex high molecular weight polymers such as polyisobutylene (PIB), polymethacrylate (PMA), and later olefin copolymers (OCP) and styrene isoprene polymers. These microscopic polymer chains behave much like microscopic springs. They remain tightly coiled when the oil is cold, but physically expand and uncoil as the fluid heats up. This artificial expansion maintains the oil's thickness and shear strength, ensuring that the crucial lubricating film between moving metal parts does not collapse under severe thermal stress, regardless of external weather conditions. Perhaps the most significant chemical breakthrough in the history of hydraulic fluids was the introduction of extreme pressure anti-wear additives, most notably zinc dialkyl dithiophosphate, ZDDP, developed and patented in the 1940s. In high-pressure hydraulic pumps, particularly modern high-speed vane and axial piston pumps, the mechanical forces pushing the internal metal surfaces together are so extreme that the liquid oil film is frequently squeezed out entirely. This leads to catastrophic metal-on-metal contact, a state known as boundary lubrication, which causes rapid component destruction. ZDDP molecules act as microscopic chemical sentinels. When the intense, localized heat of friction occurs at the microscopic peaks of metal contact, known as asperities, the organometallic ZDDP molecule intentionally decomposes. It reacts directly with the exposed iron to form a sacrificial, solid, glassy polyphosphate tribofilm. This incredibly tough solid chemical barrier prevents the steel surfaces from micro-welding together and tearing apart, allowing hydraulic pumps to survive the blistering, sustained internal pressures of modern industry. Simultaneously, engineers had to combat the unique, deadly dangers associated with high-pressure fluid power. The U.S. military, naval fleets, and the burgeoning commercial aviation industry quickly recognized a fatal flaw: a ruptured hydraulic line spraying highly pressurized atomized mineral oil onto a hot jet engine exhaust, red-hot brake caliper, or molten metal forge would result in an immediate catastrophic fireball. To eliminate this severe flammability risk, the industry was forced to turn away from highly combustible petroleum distillates and engineer entirely synthetic, fire-resistant hydraulic fluids from scratch. In the late 1940s, a critical joint venture between the Douglas Aircraft Company and the chemical giant Monsanto resulted in the creation of Skydrol, a revolutionary synthetic fluid based on phosphate ester technology. Unlike traditional mineral oils, these synthetic phosphate esters possessed incredibly high auto-ignition temperatures and inherently resisted sustained combustion, even when sprayed directly into an ignition source. Skydrol, distinctively dyed purple or green to aid mechanics in leak detection, became the absolute lifeblood of modern commercial aviation. It safely and reliably powered the primary flight controls, massive landing gear actuators, and anti-lock braking systems of airliners manufactured by Boeing and Airbus, drastically reducing the terrifying threat of in-flight hydraulic fires. From organic phosphate esters to synthetic polyalpha olefins, PAOs, developed to withstand the extreme cold of high-altitude flight, the continuous aggressive evolution of synthetic chemistry ensured that the hydraulic fluid itself became a highly engineered active component of the machine, as meticulously designed and critical to survival as the hardened steel from which the aircraft was forged. The ultimate multiplier, Bramah's press and the forging of heavy industry. While the efficient transmission of power and the chemical perfection of the fluid were crucial milestones, the true awe-inspiring magic of hydraulics lay in its profound ability to mathematically multiply force. This concept, derived directly from Pascal's theoretical physics, was famously realized by the English inventor Joseph Bramah. In 1795, Bramah secured a patent for the hydraulic press, a machine that translated 17th-century hydrodynamic theory into earth-shattering mechanical reality, fundamentally changing what human beings were capable of building. The principle behind Bramah's press was astonishingly simple in its geometry, yet immensely powerful in its application. It utilized two fluid-filled cylinders of vastly different diameters, connected securely by a high-pressure pipe. A small, easily driven piston operated within the narrow cylinder, while a massive, heavy ram operated within the wide cylinder. Because the water inside the system was incompressible, pushing down on the small piston with a modest amount of human force generated a specific measurable pressure within the trapped fluid. According strictly to Pascal's law, this exact pressure was transmitted equally to every single square inch of the much larger ram. Because the larger ram possessed a significantly greater surface area, the total upward force exerted upon it was multiplied by the exact ratio of the two pistons. A single man operating a simple hand pump could effortlessly lift weights that previously would have required enormous teams of draft horses, massive structural levers, or complex friction-heavy gear reduction systems. However, the theoretical brilliance of Bramah's press was nearly doomed to failure by a severe practical limitation: the inability to seal the high-pressure fluid within the metal cylinders. In the late 18th century, the science of sealing moving mechanical parts was incredibly primitive. Engineers relied heavily on traditional packing glands stuffed with braided hemp soaked in animal fat, tightly wound rope, or rudimentary swelling wooden plugs. When Bramah attempted to operate his early press prototypes, the extreme hydrostatic pressure generated within the fluid simply blew past these crude seals. The water sprayed violently out of the cylinders, instantly dissipating the multiplied force and rendering the machine useless. The metal-to-metal machining tolerances of the era were far too loose, and traditional natural packing materials were completely obliterated under the immense compressive strain. Bramah's press, and arguably the immediate future of high-pressure fluid power, was saved from obscurity by a young, brilliant mechanic in Bramah's employ named Henry Maudslay. Maudslay recognized that static, rigid seals crammed into a gap would always eventually fail under dynamic, fluctuating pressure. His solution was a stroke of unparalleled engineering genius: the self-tightening cup leather seal. Maudslay designed a thick circular collar of treated leather, carefully shaped like a U-cup, which was precisely fitted around the base of the main hydraulic ram. Crucially, the open end of the U-shaped cup was oriented to face directly into the pressurized fluid. As the hand pump forced water into the cylinder and the internal pressure began to rise, the fluid physically entered the U-shaped channel of the leather. This fluid pressure forced the flexible lips of the leather to flare outward against the metal walls. The higher the hydrostatic pressure climbed, the harder the fluid forced the leather against the polished steel walls of the cylinder and the sliding ram, creating a perfect, impenetrable barrier. Maudslay had successfully created a dynamic, pressure-energized seal that utilized the very pressure of the system it was containing to maintain its own integrity. When the pressure was released by the operator, the leather relaxed slightly, allowing the massive ram to descend smoothly without excessive binding friction. This single brilliant invention, born in a dusty London locksmith shop, proved definitively that small amounts of fluid could multiply force to move mountain-sized loads without leaking. The successful implementation of Bramah's press, secured by Maudslay's seal, triggered an absolute revolution in machine tools, civil engineering, and heavy manufacturing. For the first time in history, engineers possessed a machine capable of generating the immense, perfectly controlled compressive forces required to stamp thick steel plates, forge massive iron engine components, and hoist impossible loads with slow, deliberate precision. The hydraulic press became the beating heart of 19th and 20th century metallurgy. It shaped the raw materials that built the transcontinental railways, bent the thick armor plating of the ironclad navies, and formed the structural steel girders of the modern skyscraper city. It laid the vital foundation for the mass production of uniform, interchangeable metal parts, forever changing the scale and landscape of industrial manufacturing. To truly grasp the astonishing scale of force multiplication made possible by these foundational principles, one must look at the extreme applications of the 20th century. Consider the majestic ocean liners of the early 1900s, such as the RMS Titanic. Steering a vessel weighing over 50,000 tons through the North Atlantic required immense force. The ship utilized a massive steam-powered steering engine, but controlling those steam valves from the ship's wheelhouse hundreds of feet away was achieved using a sophisticated hydraulic telemotor system developed by Brown Brothers and Company. The helmsman turned the ship's wheel, which drove a small hydraulic piston. The incompressible fluid transmitted this movement through thin copper pipes running the length of the ship, actuating a receiving piston at the stern that commanded the massive steering engines to turn the multi-ton rudder, proving that hydraulic multiplication could conquer the inertia of the largest moving objects on Earth. The scale expanded even further in terrestrial mining. The Bagger 288, built by the German company Krupp in 1978, stands as one of the largest land vehicles ever constructed. Weighing a staggering 13,500 tons and stretching over 200 meters long, this monstrous bucket wheel excavator relies on vast, complex networks of heavy-duty hydraulic drives, massive pressurized cylinders, and hydrostatic transmissions to propel its crawler tracks, rotate its colossal cutting wheel, and move an incomprehensible 240,000 cubic meters of earth every single day. Even the sheer, terrifying brute force required to manipulate the primary armaments of the world's most powerful warships relied entirely on fluid power. The USS Iowa-class battleships commissioned during World War II were equipped with massive Mark VII 16-inch 50-caliber naval guns. These guns, weighing over 260,000 pounds each, required immense, highly controlled power to load. Sailors utilized massive hydraulic rammers, heavy fluid-driven pistons operating on the exact principles codified by Bramah to swiftly and safely shove armor-piercing projectiles weighing up to 2,700 pounds, followed by hundreds of pounds of explosive powder bags deep into the breech of the gun before firing. Furthermore, the violent, city-leveling recoil of firing these weapons was safely absorbed by massive hydraulic cylinders, proving that fluid could not only multiply force to do work, but could perfectly absorb and dissipate the most destructive kinetic energies unleashed by humanity. The precision leap, from Elmwood joints to sub-micron servo valves. The evolution of hydraulic power is inextricably linked to the relentless, centuries-long pursuit of tighter manufacturing tolerances and superior materials. The ability to contain, direct, and utilize fluid at immense pressures relies entirely on the structural integrity of the system's seals and the microscopic precision of its control valves. The history of sealing technology is a profound testament to this struggle. Ancient civilizations utilized available organic materials, clay, plaster, and animal fats to seal early irrigation systems and the magnificent stone aqueducts of the Roman Empire. Even the earliest known uses of the cylinder and piston concept, such as the ancient Mesopotamian cylinder seals rolled in wet clay, demonstrated an early human understanding of using cylindrical geometry for control and impression. However, as society moved toward pressurized networks, the materials lagged dangerously behind the ambition. The early Victorian water networks, such as the aforementioned London Bridge Waterworks, relied heavily on hollowed-out elm logs connected end-to-end. These wooden joints were meant to swell with moisture to create a rudimentary organic seal, but they were a complete engineering nightmare. They leaked profusely, rotted quickly, and ruptured violently when subjected to fluctuating urban pressures. Even well into the 19th century, as robust cast-iron pipes replaced rotting wooden conduits, the internal dynamic seals of massive steam engines and early hydraulic pumps remained incredibly primitive. Engineers relied on heavily compressed packing glands stuffed with braided hemp, rope, and leather soaked in tallow or whale oil. While Henry Maudsley's brilliant cup leather seal was a monumental, necessary improvement for heavy, slow-moving industrial rams, natural leather was fundamentally flawed. It degraded rapidly over time, suffered from severe chemical incompatibility with the new mineral oils being introduced, and was utterly unsuited for the high-speed, high-temperature, continuous-duty hydraulic systems emerging in the early 20th century. The materials revolution of the 1900s transformed the sealing landscape entirely. The discovery and widespread industrial application of vulcanized natural rubber provided a much more uniform and resilient sealing material for steam and water. However, this was quickly superseded by the rapid invention of synthetic elastomers, largely driven by the extreme material demands of the aviation sector and the military prior to and during World War II. Chemists successfully engineered incredibly robust synthetic rubber compounds, such as nitrile, NBR, neoprene, and eventually advanced fluorocarbons, FKM, and polyurethanes. These synthetic polymers were custom-tailored at the molecular level to withstand blistering operational temperatures, resist the highly corrosive chemical degradation of synthetic aviation hydraulic oils like Skydrol, and maintain their vital elasticity without taking a permanent leak-inducing compression set under extreme mechanical pressure. The advent of the simple but brilliant elastomeric O-ring alongside highly complex multi-lipped U-cups and heavy-duty wiper seals finally allowed engineers to completely and dynamically seal hydraulic cylinders operating at thousands of pounds per square inch without a single drop of fluid leakage. However, the ultimate control and finesse of fluid power is dictated not merely by the seals that contain it, but by the precision valves that direct its flow. The evolution of the hydraulic valve represents one of the most significant and demanding leaps in precision metallurgy and manufacturing in human history. Early industrial valves, such as the basic manually operated gate and globe valves of the late 19th century, were cast from basic iron or soft bronze. They were incredibly heavy, agonizingly slow to operate, and their internal sealing components suffered from rapid destructive erosion when exposed to high-velocity fluid flow. As industrial temperatures and pressures increased dramatically in the 20th century, the metallurgy of valves shifted completely. By the mid-20th century, valve bodies were being cast from high-strength forged steel to prevent explosive ruptures. More importantly, the critical internal components that actually controlled the fluid, the stems, seats, and spools, were forged from advanced, highly durable alloys. Materials like Monel, a highly corrosion-resistant copper-nickel alloy, and heat-treated martensitic 400 series stainless steels became the industry standard. To survive the violent, continuous cutting action of high-velocity, high-pressure fluid, the edges of these components were frequently hard-faced with exotic materials like stellite, a cobalt-chromium superalloy that offered near-diamond hardness and supreme, uncompromising wear resistance. Yet, superior metallurgy was rendered entirely useless without equally superior machining capabilities. The absolute heart of any modern high-performance hydraulic system is the directional control spool valve. This complex valve consists of a highly polished, multi-tiered cylindrical spool that slides rapidly back and forth within a stationary, perfectly machined metal sleeve or valve body. The lands, the precisely raised outer diameter portions of the spool, must block the high-pressure fluid ports in the sleeve with absolute microscopic perfection, while the recessed grooves allow pressurized fluid to pass to the actuators when the spool is shifted. Because these valves regularly operate at pressures exceeding 3,000 psi, even a microscopic, invisible gap between the spool and the sleeve will result in severe internal fluid leakage, catastrophic loss of system pressure, and highly erratic machine control. Conversely, if the fit between the two metal parts is too tight, the microscopic thermal expansion of the steel during operation or the presence of a single microscopic particle of fluid contamination will cause the valve to bind and seize catastrophically in mid-operation. In the early 20th century, achieving this perfect frictionless seal without using highly degradable rubber O-rings on the moving spool was an agonizingly slow, incredibly demanding process. Machinists relied exclusively on the tedious manual art of hand lapping. A highly skilled master craftsman would coat the steel in a fine abrasive diamond or silicon carbide slurry. They would then manually twist, push, and pull the spool back and forth inside the valve sleeve for hours, literally grinding the two unique parts together at a microscopic level until they formed a perfectly matched gas-tight set. While this manual process produced an exceptionally tight seal, it was incredibly labor-intensive, generated highly inconsistent bore geometries from valve to valve, and meant that internal parts were completely non-interchangeable. If a single spool was scratched or broken in the field, the entire valve assembly had to be discarded and replaced. The extreme technological demands of the Second World War and the subsequent dawn of the supersonic aerospace age shattered these manufacturing limitations forever. The absolute necessity to precisely control the flight surfaces of supersonic jets, rapidly adjust the trajectories of guided missiles, and aim complex radar arrays led to the invention of the Electro-Hydraulic servo valve. Invented by the brilliant engineer Bill Moog in 1951, the servo valve was a technological marvel that forever changed the landscape of automation. It utilized a minuscule low-voltage electrical signal, such as from a pilot's joystick, a gyroscope, or an early analog computer, to actuate a highly sensitive permanent magnet torque motor. This tiny motor moved a delicate flapper mechanism, which brilliantly utilized the system's own hydraulic pressure to shift the massive main steel spool. For the first time in engineering history, microscopic electrical currents could precisely command massive, bone-crushing hydraulic forces with lightning-fast dynamic response, forming the ultimate seamless bridge between the digital brain of a computer and the mechanical muscle of the physical world. To mass-produce these aerospace-grade servo valves with absolute reliability, the global manufacturing industry had to undergo a profound revolution. The highly variable, laborious process of hand-lapping was gradually replaced by ultra-precision automated grinding and honing. The advent of computer numerical control, CNC, machining in the 1970s and 1980s brought flawless, repeatable digital exactitude to the factory floor. Advanced centerless grinders, internal bore grinders, and highly rigid cylindrical grinding machines operating on frictionless hydrostatic guideways and guided by real-time laser measurement systems could cut and shape hardened steel with previously unimaginable precision. Today, high-performance hydraulic valve spools and sleeves are manufactured using a highly automated closed-loop process known as match grinding. An advanced CNC machine measures the exact internal diameter of the finished valve sleeve and automatically adjusts its parameters to grind the corresponding spool's outer diameter to fit it perfectly. This process holds geometric tolerances of cylindricity, roundness, and concentricity to within an astonishing 1.25 microns, approximately 0.00005 inches, representing merely a fraction of the width of a single human hair. Furthermore, the surface finish of these components is machined to a mirror-like 0.1 micrometers RA. This breathtaking level of manufacturing precision ensures that modern hydraulic valves operate with zero mechanical backlash, minimal sliding friction, and virtually zero internal leakage, no matter whether they are directing the steering gear of a supertanker, extending the boom of a massive construction crane, or making microsecond adjustments to the flight controls of a supersonic stealth bomber. The evolution of hydraulic systems encapsulates the relentless, brilliant trajectory of human innovation. What began as an opportunistic, primitive harvesting of the Thames River currents to spin wooden water wheels has matured into a hyper-precise, highly chemical discipline of fluid power engineering. By untethering power generation from the geography of rivers via Armstrong's brilliant accumulators, and by decentralizing industrial energy distribution through the masterful application of Pascal's law, engineers dismantled the rigid, dangerous constraints of the early Industrial Revolution. The mechanical genius of Joseph Bramah and Henry Maudslay proved that fluid pressure could act as the ultimate force multiplier, granting humanity the sheer brute strength required to forge the heavy infrastructure of the modern world. Yet brute strength alone was insufficient. It was the alchemical scientific transition from corrosive freezing water to highly engineered additive-rich synthetic oils that ensured these machines could survive the extreme thermal and mechanical environments of the 20th century. Finally, the mastery of modern materials science and the advent of sub-micron CNC precision machining elevated hydraulic valves from leaky, rudimentary stops to lightning-fast, computer-controlled conduits of pure energy. Today, the invisible blood of highly specialized fluid coursing rapidly through precision-ground steel arteries remains the undisputed muscle behind global infrastructure, silently and flawlessly holding the weight of the modern world. As the decades progressed, the demands placed upon hydraulic systems grew exponentially, pushing the technology from the ground into the upper atmosphere. The commercial aviation industry forced a monumental shift toward extreme 5,000 pounds per square inch systems, shedding thousands of pounds of dead weight to make modern super jumbo jets economically viable. These high-altitude networks evolved into incredibly complex, redundant circuits that now function as the infallible nervous systems of modern passenger jets, governed by advanced mathematical voting algorithms and electro-hydraulic actuators. Finally, this continuous line of innovation reaches its current zenith in the 2026 era of space exploration, where the aerospace industry has entirely discarded subtractive machining. Today, through the magic of three-dimensional metal printing, engineers are growing hydraulic manifolds layer by layer without internal supports, reducing weight by 70% and enabling the next generation of SpaceX rockets to conquer the cosmos. To understand the modern world and our expansion into the next, one must understand the profound evolution of fluid power. The post-war paradigm shift, retiring the mechanical cable for the high-pressure piston. To truly appreciate the revolution brought about by hydraulic power in the mid-20th century, one must first understand the severe limitations of the era that preceded it. The early mechanized earth-moving equipment, which rose to prominence during the late 19th and early 20th centuries, relied heavily on steam and early diesel engines, connected to an incredibly complex array of mechanical linkages, friction clutches, winding drums, and thick steel cables. These mechanical cable-driven systems, while miraculous for their time and instrumental in constructing monumental infrastructure, were plagued by inherent physical drawbacks. Cable-operated shovels and excavators functioned through a system of tension and mechanical advantage. The resulting motions of the digging buckets and lifting booms were characteristically jerky, abrupt, and entirely lacking in finesse. Operators had to constantly fight the machinery, engaging and disengaging heavy clutches to muscle the equipment into position. Beyond the lack of precision, these mechanical systems were highly susceptible to catastrophic and dangerous failures. The steel cables were under immense, constant tension while lifting heavy loads of rock and soil. They required relentless maintenance, lubrication, and inspection. When a cable inevitably frayed and snapped under the strain, it would whip through the air with lethal velocity, frequently resulting in severe injuries or fatalities on the job site. Furthermore, the sheer physical toll on the human operators was immense. The constant jarring, vibration, and mechanical shock transferred directly through the levers into the operator's hands and spine, leading to rapid fatigue and chronic injury. The end of the Second World War signaled a desperate global need for rapid reconstruction and unprecedented infrastructure expansion. The limitations of cable-driven equipment could no longer be tolerated if the ambitious timelines of post-war development were to be met. The breakthrough that answered this call was not a new mechanical invention, but the practical, mobile application of a scientific principle formalized in the 17th century by the French mathematician and physicist Pascal. Pascal's law dictates that whenever pressure is applied to a confined, incompressible fluid, that pressure is transmitted equally and undiminished in every direction throughout the fluid. By the early 1950s, engineers successfully harnessed this principle, stripping away the bulky cables, winches, and massive gearboxes of heavy machinery, and replacing them with tightly sealed networks of pressurized oil. The transition to hydraulics meant that instead of winding a steel rope around a drum to lift an excavator boom, an operator could simply open a valve. This action directed highly pressurized hydraulic fluid into a heavy-duty steel cylinder, forcing a piston to extend outward with immense, unstoppable power. The fluid, being virtually incompressible, translated the engine's energy directly into physical movement. This provided a perfectly smooth, continuous, and highly controlled application of force. The global shift was ignited by several pioneering innovations occurring simultaneously around the world. In France, the story began in the town of Berberie in the Oise region, where Georges Bataille had founded the Poquelin Company in 1927. Originally dedicated to agricultural equipment and transport trailers, the company witnessed a massive leap forward when Pierre Bataille created the first hydraulic excavator design in 1950. This culminated in the introduction of the Poquelin TU in 1951, widely recognized as the first commercially successful fully hydraulic excavator, though it was mounted on a two-wheeled trailer and could not yet spin a full 360 degrees. By the 1960s, Poquelin had introduced the TY-45, a fully rotating wheeled hydraulic excavator painted in their distinctive ruby red, which became a symbol of the post-war European construction boom, featuring ergonomic cabs and advanced hydraulic motors that completely redefined urban construction. Across the Atlantic in the United States, a similar revolution was taking place, driven by two Dutch immigrant brothers, Ray and Coop Furwetta. Settling in Cleveland, Ohio, they formed a construction company that handled road building and site preparation. During the late 1930s and early 1940s, the brothers faced severe labor shortages as men were drafted into military armament factories to support the war effort. Roadside finishing work, which required men to manually grade steep embankments with hand shovels and pikes, became nearly impossible to staff. By using their incredible ingenuity, the Furwetta brothers rented a garage in Beechwood, Ohio, and developed a fully hydraulically powered telescopic boom machine to replace the missing laborers. When Ray's wife, Evelyn, saw the machine working, she remarked that it looked like a giant using its arms to grade the earth and its hands to do all the work, leading to the legendary brand name, Gradall. Because it utilized hydraulics rather than cables, the Gradall excavator could reach under bridges, avoid overhead power lines, and sculpt the earth with a delicate precision that cable shovels could never replicate. Meanwhile, in Japan, the post-war reconstruction effort required massive amounts of new equipment. While early machinery relied on cable-operated shovels, the realization that fluid power was the future led to Hitachi to develop the UH-03 in 1965. This was the first hydraulic excavator developed entirely using domestic Japanese technology, utilizing an innovative two-pump, two-control valve hydraulic system that drastically improved operator responsiveness and machine efficiency. The advantages of these new hydraulic pistons over mechanical cables were overwhelming. Hydraulic machines could dig much deeper into the earth, lift vastly heavier loads, and operate for much longer hours without the constant mandatory maintenance interruptions required by fraying ropes and grinding gears. Most importantly, the rapid response and fine-tuned precision of hydraulic controls allowed operators to manipulate massive buckets of earth with a delicate accuracy. Operators could smoothly grade surfaces, carefully navigate around underground utility lines, and cushion the movements of the machine. By the close of the 1960s, the transition was absolute. The clattering, dangerous, cable-driven shovels had rapidly faded into history, entirely replaced by the smooth, hissing power of fluid mechanics. The external gear pump and the architecture of urban expansion. As the mid-20th century progressed, recovering nations embarked on some of the largest public works projects in human history. In the United States, the post-war economic boom and the sudden affordability of the automobile created an absolute necessity for better roads. This culminated on June 29, 1956, when President Dwight B. Eisenhower, recuperating from an intestinal ailment at Walter Reed Army Hospital, privately signed the Federal Aid Highway Act of 1956. This colossal undertaking authorized the construction of the Interstate Highway System, a staggering network of multi-lane, limited-access expressways spanning tens of thousands of miles across diverse and unforgiving terrain. To physically reshape the landscape on such a colossal scale, the construction industry required machinery that was not only powerful, but utterly relentless. The dominant force behind this era of urban expansion was the refinement and mass implementation of the external gear pump, a relatively simple yet profoundly effective mechanism that served as the beating heart of these new hydraulic behemoths. For a hydraulic system to function, it requires a continuous, highly pressurized flow of fluid to actuate the pistons. This is the sole purpose of the hydraulic pump, which converts the mechanical rotational energy of a bulldozer or excavator's massive diesel engine into fluid power. The external gear pump emerged as the undisputed champion of mobile construction equipment due to its remarkable durability, high pressure capacity, and mechanical elegance. The architecture of the pump is remarkably straightforward. It consists of two identical interlocking gears housed within a precisely machined, tightly fitting metal casing. One gear, known as the driver gear, is connected directly to the engine's drive shaft. As the engine turns the driver gear, its teeth engage with the second gear, known as the driven gear or idler, causing it to rotate in the exact opposite direction. The magic of fluid transfer occurs at the outer edges of these rotating gears. As the interlocking teeth of the two gears come out of mesh on the intake side of the pump, they create a rapidly expanding cavity. This sudden increase in volume creates a localized vacuum, which actively draws hydraulic fluid from the machine's reservoir into the pump housing. The thick hydraulic oil flows into the spaces between the gear teeth. As the gears continue to rotate, the fluid is trapped between the teeth and the tightly toleranced inner wall of the metal casing. The oil is then carried around the outer periphery of the gears, from the intake side to the discharge side. It is critical to understand a fundamental physical principle of this design. The fluid does not pass through the center where the gears mesh together. The tightly interlocking teeth form a nearly perfect mechanical seal that prevents any liquid from flowing backward through the center. As the oil reaches the discharge port, the teeth of the two gears begin to mesh together once again. This meshing violently reduces the available volume in the gear valleys, forcing the trapped hydraulic fluid out of the pump and into the high-pressure lines of the system. Because the gears rotate at high speeds, usually thousands of revolutions per minute, this process delivers a remarkably smooth, pulse-free, and continuous flow of pressurized oil that is directly proportional to the rotational speed of the engine. To measure the performance of these pumps, engineers look at the pressure differential across the pump and the volumetric flow rate, linking them through a mathematical concept known as hydraulic resistance. However, because the thick hydraulic fluid heats up rapidly under immense pressure, engineers often utilize a specialized calculation called the hydraulic parameter, which factors in the dynamic viscosity of the fluid to ensure the pump performs consistently regardless of the operating temperature. To further reduce the acoustic noise and physical vibration of the pumping action, engineers sometimes utilized helical or herringbone gear designs. In a standard spur gear, the teeth are cut straight across, but in a helical design, the teeth engage and disengage gradually at an angle. This results in a whisper-quiet operation even under immense loads, while a V-shaped herringbone pattern is used to perfectly cancel out the resulting axial forces pushing against the pump casing. The external gear pump was the perfect solution for the dirty, grueling environment of earth moving. These pumps were exceptionally robust, capable of easily sustaining the moderate to high pressures required to force a bulldozer blade through compacted clay or lift tons of solid rock. By integrating these tireless external gear pumps into the chassis of heavy machinery, engineers empowered construction crews to flatten hills, carve out immense valleys for highways, and dig the deep foundations required for modern skyscrapers. This immense power was critical for the new highway system, especially when the Department of Defense demanded that the new overpasses be built with a minimum vertical clearance of 16 feet for the transport of massive military equipment, such as the Atlas intercontinental missile across the country. Raising these massive concrete bridge decks required extraordinary hydraulic force. Without the continuous high-pressure fluid flow provided by the external gear pump, the rapid urban and suburban expansion of the late 20th century simply would not have been physically possible. The miracle of miniaturization, liberating hydraulics from the factory floor. While the transition to fluid power revolutionized earth-moving, the physical integration of these systems into mobile vehicles required a profound engineering leap known as miniaturization. In the late 19th and early 20th centuries, hydraulic power was already a well-established industrial force, but it was strictly confined to massive stationary factory settings. Early hydraulic presses, used for forging steel or shaping heavy industrial components, were colossal structures that often occupied entire buildings. These early systems relied on water or low-pressure fluids pumped by massive, room-sized steam engines. The idea of taking the immense crushing power of a factory press and shrinking it down to fit within the narrow engine compartment of a tractor or the rotating cab of an excavator seemed at the time to be a physical impossibility. The sheer size of the components required to generate and contain high pressures made mobile applications entirely impractical. The liberation of hydraulics from the factory floor was largely spearheaded by visionary engineers and self-taught mechanics, most notably Harry Franklin Vickers, who is celebrated today as the father of industrial hydraulics. Born in the rugged town of Red Lodge, Montana in 1898, Vickers possessed no formal engineering training, yet he possessed an innate, brilliant understanding of mechanics and fluid dynamics. After serving in the U.S. Army Signal Corps during World War I, where he was exposed to early electronics, Vickers returned to California and established a general machining business. His trajectory changed forever when the famous author and sportsman Zane Grey brought a large saltwater fishing reel into Vickers' shop for repairs. Grey was so profoundly impressed by the young mechanic's brilliant mind that he personally paid for professors from the University of South Carolina to tutor Vickers in advanced calculus and engineering principles at night. Armed with this theoretical knowledge, Vickers tackled the problem of hydraulic power density. He realized that for fluid power to be useful in mobile applications, the industry needed to dramatically increase the power output of the components while radically shrinking their physical footprint. In the 1920s, he invented the first practical hydraulic steering system, but the automotive industry was not yet ready for his advanced concepts. Instead, he focused his company, Vickers Inc., in Detroit, on creating standardized, highly efficient components that could be applied across multiple heavy industries. His crowning achievement was the invention of the balanced hydraulic vane pump. Early hydraulic pumps suffered from severe internal pressure imbalances. High-pressure fluid on one side of the pump would exert tremendous lateral force against the internal rotor, resulting in rapid wear on the bearings and strictly limiting the maximum pressure and speed the pump could achieve. Vickers ingeniously redesigned the internal architecture to create a pump with 2 fluid strokes per revolution. By doing this, the high-pressure zones on one side of the pump were perfectly opposed and canceled out by equal high-pressure zones on the exact opposite side of the rotor. This brilliant balancing act completely neutralized the radial forces, eliminating the severe bearing loads. Suddenly, engineers had access to a highly compact, incredibly durable pump that could spin at high speeds and generate massive fluid pressure while occupying a fraction of the space of older designs. Simultaneously, the mid-20th century saw the rapid refinement of other pump architectures, notably advanced by companies such as Denison Hydraulics, originally founded as a motor company in Ohio before pivoting to fluid power. These companies perfected the axial piston pump, which arranged a series of small pistons in a circular array within a rotating cylinder block. A precisely angled swash plate would drive these pistons rapidly back and forth as the block rotated, drawing in fluid and compressing it to extreme pressures. This design inherently allowed for incredibly high pressure thresholds and the ability to vary the volume of fluid being pumped without changing the engine speed, all contained within a remarkably tight cylindrical envelope. For his monumental contributions to the miniaturization and widespread industrialization of these fluid systems, Harry Vickers was awarded the highest honor of the American Society of Mechanical Engineers, the ASME Medal, in 1956. The successful miniaturization of these hydraulic power units was deeply intertwined with post-war advances in metallurgy and precision machining. Older stationary systems utilized thick, heavy cast iron to contain the fluid pressure. However, the development of high-strength steel alloys and the ability to machine parts to microscopic tolerances allowed engineers to design compact pump casings and slim hydraulic cylinders that could withstand immense internal stresses without rupturing. Tighter dimensional controls virtually eliminated internal fluid leakage, dramatically boosting the volumetric efficiency of the systems. Heavy, rigid iron pipes were replaced with high-strength, flexible rubber hoses wrapped in braided steel wire, allowing the pressurized lifeblood to be routed through the articulating joints of backhoes and the steering linkages of loaders. By shrinking the physical dimensions of the components while exponentially scaling up their pressure capabilities, engineers untethered fluid power from the stationary factory, unleashing it to roam the Earth. The 5,000 psi revolution, saving weight in modern commercial aviation. As the principles of high-pressure fluid power matured, the aerospace industry began to look toward hydraulics as a means of controlling the increasingly massive flight surfaces of commercial aircraft. However, lifting an airplane off the ground introduces a completely different set of physical constraints than pushing dirt with a bulldozer. In the realm of aviation, weight is the ultimate enemy. Any excess weight in the basic structure of an aircraft translates directly to increased fuel consumption, reduced range, and a severe decrease in revenue-generating payload capability. Therefore, the hydraulic systems powering an aircraft must be as lightweight as physically possible while still delivering the raw mechanical power necessary to deploy massive landing gears against the force of hurricane-level slipstreams and manipulate giant rudders and ailerons to steer the aircraft. For many decades, the standard operating pressure for commercial aircraft hydraulic systems was firmly established at 3,000 pounds per square inch. This standard, solidified during the technological boom of the 1950s, was primarily dictated by the strict limitations of mid-century material science. At pressures up to 3,000 psi, aerospace engineers could safely utilize relatively inexpensive, lightweight aluminum alloys to construct the miles of fluid tubing, reservoirs, and actuator casings required throughout the airframe. Pushing the internal fluid pressure beyond 3,000 psi using aluminum became unacceptably risky, as the metal was highly prone to stress fractures, metal fatigue, and catastrophic blowout failures under extreme internal forces. For a long time, 3,000 psi was the absolute sweet spot of commercial aviation, providing sufficient power for traditional passenger jets without requiring excessively heavy materials. However, the dawn of the 21st century introduced a new breed of super jumbo wide-body aircraft, most notably the European Airbus A380 and the American Boeing 787 Dreamliner. The sheer scale of these flying leviathans broke the old mathematical models of flight control. For example, the massive upper and lower rudders of the A380 alone are subjected to aerodynamic stall loads of 22.5 tons each. To physically move these enormous surfaces at the specific rapid velocities required to keep the aircraft perfectly stable, the hydraulic actuators required an unprecedented amount of mechanical power. If engineers had attempted to power the massive A380 using the legacy 3,000 psi standard, the system would have required massive, heavy hydraulic pumps to push a massive volume of fluid through huge, thick hoses running the entire length of the giant double-deck fuselage. The weight penalty of the extra fluid and oversized components would have crippled the aircraft's fuel efficiency and payload range. To solve this dilemma, aerospace engineers implemented a radical, industry-shifting upgrade, elevating the entire system pressure to a staggering 5,000 psi. To understand why this saves so much weight, one must look at the basic physics of fluid power. Mechanical power is the mathematical product of fluid pressure multiplied by the volumetric flow rate. By increasing the pressure to 5,000 psi, the system can achieve the exact same mechanical power output while simultaneously reducing the volume of fluid flowing through the system by a staggering 40%. This drastic reduction in fluid flow rate triggered a cascade of massive weight-saving miniaturization throughout the entire aircraft. Because the system required far less fluid volume to do the same amount of work, the engine-driven pumps could be significantly downsized. A traditional 3,000 psi system on an aircraft of that size would require a pump capable of moving 70 gallons of fluid per minute. The new 5,000 psi system reduced this requirement to only 42 gallons per minute, resulting in an immediate 20% weight reduction for the pump unit itself. More importantly, the reduction in flow volume allowed engineers to dramatically shrink the physical diameter of the miles of hydraulic piping. And conventional inlet hose that would traditionally require a thick 3-inch diameter was shrunk down to a sleek 2-inch diameter. When you multiply this volume reduction across the 250 to 500 individual fittings, the manifolds and the miles of tubing snaking through the wings and fuselage, the weight savings become monumental. The Airbus A380 achieved an astonishing total weight saving of approximately 2,500 pounds simply by transitioning to the higher pressure architecture. To achieve this required a fundamental shift in materials and sealing technology. Because legacy aluminum tubing would violently rupture at 5,000 psi, the aviation industry had to rely almost exclusively on high-strength titanium and advanced stainless steel alloys to contain the immense pressure. While steel and titanium are inherently heavier than aluminum per cubic inch, the sheer reduction in the physical size and volume of the components more than offset the material density penalty. This transition also required advanced computational fluid dynamics to carefully design the internal flow paths to minimize pressure drops around the tighter corners of the much smaller passages. Furthermore, engineers had to implement advanced elastomeric seals in place of traditional metal-to-metal seals within the cylinder blocks and pistons to prevent high-pressure weeping. To achieve this, companies like Eaton Corporation leveraged their vast experience in designing 5,000 psi military hydraulic systems for the F-18 fighter jet and the V-22 Osprey tilt rotor, proving that by squeezing the fluid harder, the commercial aerospace industry could effectively squeeze thousands of pounds of dead weight out of the sky. The aircraft nervous system, redundant circuits, and the logic of aviation safety. In the realm of commercial aviation, the hydraulic system is the physical manifestation of the pilot's intent. When a pilot pulls back on the yoke or adjusts a pedal, it is the hydraulic fluid that translates those delicate inputs into the raw, crushing mechanical force required to push giant elevators and rudders against the roaring aerodynamic resistance of the sky. Because the loss of these primary flight controls would result in the immediate, uncontrollable, and catastrophic loss of the aircraft, the physical plumbing and electronic architecture of aviation hydraulics have evolved into a staggeringly complex, fail-safe network. This network closely mirrors the biological redundancy and instant reflexivity of the human nervous system. The foundational philosophy of aviation safety is that no single point of failure can ever be allowed to doom the aircraft. Therefore, a modern wide-body passenger jet never relies on a single monolithic hydraulic system. Instead, the fluid power architecture is built upon a foundation of deep, uncompromising physical and functional segregation. The total hydraulic power of the aircraft is divided into multiple completely independent closed-loop subsystems. Historically, this meant an architecture of 3 completely separated hydraulic circuits, often designated as green, blue, and yellow, or systems A, B, and C. More recently, with aircraft like the Airbus A380, this evolved into a brilliant 2H2E architecture. 2 traditional hydraulic circuits backed up by 2 completely independent electrical circuits powering localized actuators, providing unprecedented resilience against damage. Each of these segregated circuits acts as an independent organism. They possess their own dedicated reservoirs, their own engine-driven and electric backup pumps, and their own completely isolated networks of titanium tubing. Crucially, these tubes are physically routed through entirely different geographic corridors of the aircraft's fuselage and wings. This spatial segregation ensures that a localized catastrophic event, such as a turbine blade exploding outward from an engine casing, cannot sever all the hydraulic lines simultaneously. The profound necessity of this physical segregation was proven on November 4, 2010, when Qantas Flight 32 and Airbus A380 departed from Singapore. Shortly after takeoff, a microscopic manufacturing defect in an oil feed pipe deep inside the No. 2 Rolls-Royce Trent 900 engine led to a fatigue crack. The oil leaking weakened a turbine drive arm until it fractured, causing the massive turbine disc to overspeed and shatter. Hundreds of pieces of high-energy shrapnel blasted through the engine casing, tearing through the left wing and fuselage, severing roughly 650 wires and completely crippling several hydraulic pumps and fuel systems. Despite experiencing a level of cascading damage that exceeded the manufacturer's worst-case scenarios, the deep redundancy of the A380's 2H2E architecture allowed the flight control computers to seamlessly bypass the shredded systems and route control authority through the surviving electric and hydraulic circuits. The crew maintained perfect control and safely landed the crippled Leviathan without a single injury to the 469 souls on board, an absolute triumph of fail-safe fluid power design. The brilliance of this redundant architecture relies heavily on how surviving systems interact during a mechanical emergency. If a pump fails on one system, that circuit loses its pressure. To prevent the loss of those flight surfaces, the aircraft must share power between the systems. However, sharing is incredibly dangerous. If the dead system lost pressure because of a ruptured pipe, pumping fluid from a healthy system into the dead one would simply pump all the remaining fluid out of the hole, killing both systems and starving the aircraft of control. Therefore, the systems must be able to share mechanical energy without ever mixing their fluid. This miraculous feat is primarily achieved by a component known as a Power Transfer Unit, or PTU. A PTU functions very much like an automatic transmission, but it runs entirely on fluid pressure. It sits between 2 independent hydraulic circuits. If the green system loses its pump and its pressure drops, the PTU automatically engages. It uses the highly pressurized fluid from the healthy yellow system to rapidly spin a hydraulic motor. This motor is physically connected via a solid metal drive shaft to a pump located inside the dead green system. As the shaft spins, the pump repressurizes the green system's fluid. The healthy system has effectively reached across the boundary to mechanically revive the dead system without transferring a single drop of fluid, isolating any leaks and protecting the remaining healthy circuits. Passengers flying on Airbus A320 family aircraft frequently hear the PTU working. It produces a highly distinctive, repetitive barking dog or groaning sound from beneath the cabin floor during taxiing, when the engine pumps are turned on or off and the PTU tests its pressure differentials. However, perfectly segregated physical plumbing is useless if the flight control computers command the actuators to do the wrong thing. Modern fly-by-wire aircraft utilize dozens of redundant sensors to monitor airspeed, pitch, and angle of attack. Because sensors can degrade, ice over, or fail, sending dangerously erratic data, aerospace engineers developed highly sophisticated mathematical logic to determine the truth. The cornerstone of this fault-tolerant software is the mid-value select algorithm. If a critical metric is measured by 3 independent sensors, the flight computer continuously ingests the data from all 3. The computer does not calculate the average of the 3 numbers. Averaging is incredibly dangerous. If one broken sensor suddenly reads a massive extreme value, it will violently skew the average, potentially tricking the flight computer into commanding a fatal dive. Instead, the mid-value select algorithm instantly isolates and outputs the exact median or middle value. If sensor A reads 10 degrees, sensor B reads 11 degrees, and sensor C suddenly shorts out and reads 90 degrees, the MVS algorithm instantly dismisses the extreme outlier of 90 degrees, ignores the lowest value of 10 degrees, and utilizes the perfectly safe middle value of 11 degrees. This lightning-fast digital reflex acts as the brain of the nervous system, ensuring that the redundant hydraulic muscles only ever react to pure, accurate truth. Rise of electro-hydraulic actuators. Software precision meets fluid power. While centralized, highly redundant hydraulic systems represent the historical pinnacle of aviation safety, the relentless drive for improved fuel efficiency, reduced maintenance, and lighter airframes has pushed the aerospace industry toward a radical new paradigm, the electro-hydraulic actuator, commonly referred to as the EHA. For decades, the reliance on a central hydraulic reservoir required miles of heavy, pressurized tubing snaking continuously throughout the entirety of the airframe. This traditional fluid-by-wire approach carried immense weight penalties, required constant and tedious maintenance to hunt down and repair microscopic fluid leaks, and demanded massive amounts of engine power to keep the central pumps continuously spinning and pressurized, even during long straight portions of the flight, when the control surfaces were entirely stationary. The advent of EHA technology completely upends this architecture by entirely decentralizing the hydraulic nervous system. It replaces the heavy, archaic concept of fluid-by-wire with the incredibly efficient concept of power-by-wire. An electro-hydraulic actuator is a highly localized, perfectly self-contained mechatronic unit mounted directly at the exact point of action, such as bolted directly onto the hinge of an aileron on the wing or the massive rudder on the tail. It completely eliminates the need for central fluid reservoirs and the miles of vulnerable fluid conduits running through the fuselage. Instead, each individual EHA contains everything it needs to function within a single compact housing: a miniature, highly powerful bidirectional electric motor, a dedicated high-pressure fixed displacement pump, a tiny internal reservoir containing a very small volume of hydraulic fluid, and a symmetrical hydraulic cylinder. Because the EHA generates its own fluid pressure internally, it does not need to be connected to hydraulic hoses. Instead, it is connected to the aircraft's electrical grid via lightweight power cables. These electrical wires are exponentially lighter, vastly easier to route, and significantly less vulnerable to damage than highly pressurized hydraulic lines. The operational superiority of the EHA lies in its brilliant utilization of power on demand. In a traditional centralized system, the heavy hydraulic pumps run constantly off the main engines, bleeding away energy through fluid friction just to maintain standby pressure. In stark contrast, the electric motor within an EHA sits perfectly dormant, consuming absolutely zero energy until the exact moment motion is commanded. When the pilot or the autopilot software dictates a movement, electrical current surges into the EHA. The electric motor instantly activates, spinning the internal pump in a fraction of a second, which instantly pressurizes the localized fluid and drives the piston to push the flight surface. The moment the surface reaches its desired position, the electric motor stops, locking the fluid in place and returning to a state of zero energy consumption. This direct, immediate coupling between the electric motor and the hydraulic pump enables lightning-fast response times. It completely eliminates the slight, sluggish delays caused by long fluid travel paths and the subtle compressibility effects found in traditional miles-long hydraulic lines. Furthermore, the true revolutionary precision of the EHA is unlocked by the integration of advanced software control loops. Because the physical fluid is entirely contained and manipulated directly by the exact rotational speed of the electric motor, aerospace engineers can apply highly sophisticated software algorithms to dictate the piston's microscopic position and applied force. Historically, engineers relied on classical proportional integral derivative controllers to manage these movements. While simple and effective for linear tasks, PID controllers struggle with the highly nonlinear, unpredictable dynamics of fluid power, often resulting in slight time delays, overshooting the target position, or creating bouncy, oscillatory vibrations when holding a heavy load against the wind. To overcome this, modern researchers and flight control developers have implemented brilliant fuzzy logic controllers directly into the microprocessors of the EHA. Unlike traditional rigid mathematics, fuzzy logic excels in managing unpredictable nonlinear scenarios, allowing the actuator to adapt dynamically to changing wind resistance. By merging these concepts into a hybrid fuzzy PID controller, or fuzzy linear feedback control, engineers have created software that predicts and neutralizes fluid pressure spikes before they happen. Simulation and testing have proven that these advanced fuzzy algorithms can eliminate target overshoot completely and improve the control performance and precision of the actuator by up to 99% compared to older methods. This seamless, elegant fusion of software-driven electrical intelligence with the raw, unyielding mechanical advantage of localized fluid power represents the definitive future of aerospace actuation, saving massive amounts of energy while delivering buttery smooth control. The 2026 Orbital era, 3D printed manifolds, and the conquest of mass. As humanity extends its reach beyond the relatively thick atmosphere of Earth and out into the unforgiving vacuum of orbital mechanics, the foundational principles of hydraulics and fluid control have violently collided with the bleeding edge of metallurgy and additive manufacturing. In the extreme realm of rocketry and space exploration, mass is the ultimate unforgiving enemy. The uncompromising physics of the rocket equation dictates an exceptionally cruel reality. Every single extraneous gram of dry mass in a launch vehicle requires an exponential compounding increase in heavy, volatile chemical propellant just to break the suffocating grip of Earth's gravity. Consequently, the heavy, blocky industrial components of traditional hydraulic systems, specifically the dense metal hydraulic manifolds used to route, split, and control pressurized fluid in engine management and thrust vector control systems, have become prime targets for radical, uncompromising weight reduction. Historically, the manufacturing of a fluid or hydraulic manifold has been a strictly subtractive process. A machinist begins with a massive, heavy, solid block of raw aluminum, steel, or titanium. Using large industrial computer numerical control drilling machines, they bore intersecting lines deep into the metal block to create the internal tunnels that the fluid will flow through. However, because a physical drill bit can only bore in a perfectly straight line, the resulting internal geometry of a traditional manifold is a jagged, highly inefficient maze of sharp 90-degree right angles. When highly pressurized fluid slams into these sharp right angles, it creates immense internal turbulence, severe fluid friction, and massive pressure drops. To overcome this internal resistance, the rocket must carry heavier, more powerful pumps. Furthermore, because the channels must be drilled from the outside of the block inward, the exterior of the manifold is left riddled with entry holes that must be individually capped, sealed, and plugged. These heavy steel plugs not only add entirely useless dead weight to the rocket, but each one introduces a potential point of catastrophic leakage and structural failure under the extreme vibration of a rocket launch. By the era of 2026, the aerospace industry, spearheaded by pioneering commercial entities like SpaceX and their massive Starship launch vehicle program, has thoroughly and entirely discarded subtractive machining for these critical components. In its place, they have fully embraced the revolutionary capabilities of metal additive manufacturing, commonly known as three-dimensional printing. Utilizing highly advanced multi-million-dollar laser beam powder bed fusion (PBF-LB) printer platforms from strategic partnerships with companies like Velo 3D, aerospace manufacturers are no longer carving blocks of metal. Instead, they use arrays of incredibly high-powered fiber lasers to melt and micro-weld microscopic layers of fine metal powder, building the hydraulic and fluid components atom by atom, layer by microscopic layer from the ground up. This additive approach has fundamentally revolutionized the fluid manifold, granting engineers absolute, unconstrained geometric freedom. Because they are no longer restricted by the straight lines of a drill bit, designers can create complex, sweeping, beautifully curved internal flow paths that look more like organic biological arteries than industrial machine parts. These optimized teardrop-shaped internal channels completely eliminate the violent turbulence and pressure loss associated with right angles, dramatically enhancing the smooth, efficient flow of the fluid. One of the greatest historical challenges of metal 3D printing was the need to print internal support structures to prevent overhanging metal from collapsing or warping under the extreme heat of the laser before it could cool. However, modern additive software, such as Velo 3D's Flow software, utilizes advanced algorithms to intelligently adjust the laser power and speed based on the specific, localized geometry of the part. Combined with non-contact powder recoating blades that snowfall the metal powder rather than scraping it like a snowplow, this technology allows engineers to print massive internal channels with horizontal overhangs of less than 10 degrees, completely free of internal supports, ensuring the fluid paths remain perfectly unobstructed. The results of this manufacturing paradigm shift are mathematically staggering. By hollowing out the unnecessary bulk and optimizing the structural lattices, additively manufactured hydraulic manifolds and valve blocks achieve verified weight reductions of up to 70% compared to their conventionally machined subtractive counterparts. This monumental mass reduction is visually and mechanically evident in the rapid, aggressive evolution of the SpaceX Raptor engine, specifically the Raptor 3, which is slated to fly on the Starship Block 3 vehicle in 2026. The Raptor engine, a marvel of full-flow staged combustion running on cryogenic liquid methane and liquid oxygen, has undergone intense iterative design. Through the aggressive, industry-leading application of metal additive manufacturing, SpaceX engineers managed to take the chaotic, heavy spaghetti of external fluid pipes, secondary flow paths, and regenerative cooling circuits that burdened the early Raptor 1 and Raptor 2 engines, and print them directly into the internal structural walls of the newest engine, the Raptor 3. By seamlessly moving these fluid circuits inside the metal via additive manufacturing, SpaceX was able to completely eliminate the heavy, bulky external heat shields, the complex bolted connections, and the heavy fire suppression systems that were previously required to protect the external plumbing. The resulting Raptor 3 engine is visually stripped down, aerodynamically perfectly clean, and massively lighter, weighing in at only 1,525 kilograms while generating a staggering 280 tons of thrust at sea level. Furthermore, the relentless drive to shed mass led to the evolution of the thrust vector control systems on the Starship itself. Early iterations relied on heavy hydraulic power units to gimbal the engines and steer the rocket. By the latest generations, this was entirely replaced by an electric TVC system, replacing the heavy hydraulic fluid reservoirs entirely with precise electromechanical actuators powered by high-density batteries. This completely eliminated the risk of hydraulic fluid fires and provided the exact millisecond-level precision required to catch a falling booster from the sky. In the unforgiving, silent vacuum of space, where survival relies entirely on perfect mechatronic execution and the absolute minimization of mass, the fluid power systems of 2026 have completely shed their heavy industrial origins. From the fundamental physics equations drafted by Blaise Pascal in the 17th century to the dripping steel cable constraints of a post-war steam shovel, the evolution of fluid and hydraulic power is a breathtaking testament to humanity's relentless, unyielding drive to master and multiply physical force. By continuously miniaturizing massive pumps, embedding infallible, fault-tolerant software logic into decentralized electrical grids, and leveraging the revolutionary organic geometry of three-dimensional metal printing, fluid power has evolved from the slow, blunt instrument of earth-moving into the hyper-efficient, featherweight nervous system of our orbital expansion.